Well, welcome back to college physics. We're making some good progress in our course material here. And so we're in the second topic of this thermodynamics session. And so we'll be talking about energy and thermal processes. And I think you're starting to see that how the contact that we're have already covered, it keeps building as we move into these more complicated and more interesting areas per se. And so just keep that in mind, that it's good that we started out with the basic material that we have here with mechanics, and now we're getting into some other areas. Now we're into thermodynamics. And so what we're seeing in this figure, this is a thermogram of a house made during cold weather. And you can see where things are hotter, where things are emitting out of the house, around the windows and stuff like that, and the door, as is would be typical of what you might think would be the case. So let's go through a couple of questions that will cover the reading material, then we'll get into the main lecture, and we'll be introducing some questions as we progress there, and then have a summary. So the first one is, you have a 1 kilogram of liquid water and 1 kilogram of steam. If you want to increase the temperature of both of them by 10 degrees C, which would require more added energy? And the answer is the water. Next one, is it possible to add energy to an isolated material and not have the material's temperature change? The answer is yes. In some cases, a material's temperature will change when energy is added to the material. In other cases, materials' temperatures will not change when energy is added. So which curve would have the smallest slope? Assume no phase changes take place. The answer for this is that the temperature of water versus added energy. Areas need a cold ocean or other cold body of water often experience a sea breeze during the late morning, particularly on warm, sunny days. The process of energy transfer is most directly associated with the development of the sea breeze is, the answer is convection. You measure the temperature of two objects and one of them is warmer than the other. From this, you can conclude that none of these statements, so there's none of these is something that you can conclude from this information that is presented. Okay, well, let's start to get into this discussion on energy and thermal processes. And so just to give you a perspective, imagine what happens when two objects with different temperatures are placed on thermal contact. The temperature of the warmer object decreases while the temperature of the cooler object increases. Eventually, they will reach a common equilibrium temperature somewhere in between the initial temperatures. During this process, we say the energy is transferred from the warmer object to the cooler one. Thanks to the English physicist James Joule, who lived from 1818 to 1889, we know that decrease in mechanical energy, that is kinetic plus potential of an isolated system, is equal to the increase in internal energy of the system. Nowadays, we treat internal energy as a form of energy that can be transferred into mechanical energy and vice versa. This is the conservation of energy. So heat involves a transfer of internal energy from one location to another. So internal energy U is the energy associated with the atoms and molecules of the system, and includes kinetic and potential energy associated with the random translational, rotational, and vibrational motion of the particles that make up the system, and any potential energy bounding the particles together. Recall that the internal energy of a monotonic ideal gas is associated with the translational motion of atoms. In the special cases, the internal energy is a total translational kinetic energy of atoms. The higher the temperature of the gas, the greater the kinetic energy of the atoms, and the greater the internal energy of the gas. For more complicated diatomic and polyatomic gases, internal energy includes rotational kinetic energy and the kinetic and potential energy associated with the molecular vibrations. internal energy is also associated with the intermolecular potential energy, the quote bond energy between molecules in liquid or solid. Heat is a transfer of energy between a system and its environment due to the temperature differences between them. The symbol Q is used to represent the amount of energy transferred by heat between the system and its environment. Be careful with the language here. If a pan of water is heated on the burner of a stove, it is incorrect to say that more heat is in the water. Heat is the transfer of thermal energy, just as work is a transfer of mechanical energy. When an object is pushed, it doesn't have more energy, rather it has more mechanical energy transferred by work. In the same way, the pan of water has more thermal energy transferred by heat. So early on, heat was defined in terms of the temperature change that it produced in an object, and a separate unit of energy, the calorie, was used for heat. The calorie is defined as the energy necessary to raise the temperature of 1 gram of water from 14.5 degrees C to 15.5 degrees C. Note that the calorie, with a capital C, used to describe the energy content of food is actually a kilocalorie. The unit of heat in the US customary system, the British thermal unit, BTU, was defined as the energy required to raise the temperature of 1 pound of water from 63 degrees Fahrenheit to 64 degrees Fahrenheit. In 1948, scientists agreed that because heat, like work, is a measure of the transfer of energy, its SI unit should be a joule. The calorie is now defined to be exactly 4.186 joules. This relationship shows the mechanical equivalent of heat. This means the amount of energy required to raise the temperature of a kilogram of water is 1,186 joules. Each substance requires a different amount of energy to do the same thing. For example, the energy required to raise the temperature of 1 kilogram of copper by 1 degrees is 387 joules. So if a quantity of energy Q is transferred to a substance of mass M, changing its temperature by delta T, the specific heat C of the substance is defined by the equation given here. The table lists specific heats for several substances. As you can see, the specific heat of water is 4,186 joules per kilogram degree C. We can rearrange this equation to solve for Q. Let's do a quick example. Suppose you want to know the energy required to raise the temperature of half a kilogram of water by 3 degrees. Using our equation for Q, we get this result. Notice that when the temperature increases, delta T and Q are positive, corresponding to energy flowing into the system. When the temperature decreases, delta T and Q are negative and energy flows out of the system. So in this figure, we're looking at the circulation of air at the beach. On a hot day, the air moves above the sand, warms faster than the air above the cooled water. The warmer air flows upward due to Archimedes' principle, resulting in the movement of cooler air towards the beach. Water has a relatively high specific heat. When the temperature of a body of water decreases, for example, during winter, the water transfers energy to the air, which carries the energy landward, where the prevailing winds are forward toward the land. Off the western coast of the United States, the energy liberated by the Pacific Ocean is carried to the east, which keeps coastal areas much warmer than would be otherwise. Winters are generally cooler in the eastern coastal states because the prevailing winds tend to carry the energy away from land. The fact that the specific heat of water is higher than the specific heat of sand is responsible for the pattern of airflow at the beach. During the day, the sun adds roughly equal amounts of energy to the beach and the water, but the lower specific heat of the sand causes the beach to reach a higher temperature than the water. This means that the air above the land reaches a higher temperature than the air above the water. The dense cold air pushes the less dense hot air upward due to Archimedes' principle, resulting in a breeze from the ocean to the land during the day. Because the hot air gradually cools as it rises, it subsequently sinks setting up a circulatory pattern shown in the figure. A similar effect produces rising layers of air called thermals that can help eagles soar higher and hang gliders stay in flight longer. A thermal is created when a portion of the Earth reaches a higher temperature than neighboring regions. So here's a question. Suppose we have 1 kilogram each of iron, glass, and water, and all 3 samples are at 10 degrees C. Rank the samples from lowest to highest temperature after 100 joules of energy is added to each by heat. And so the answer is it would be water, then glass, and then iron. Because it has the highest specific heat, water has the smallest change in temperature. Glass is next and iron is last. So in this one, suppose you have 1 kilogram each of iron, glass, and water, and all are raised by 10 degrees C. Rank them from least to greatest amount of energy transferred by heat if enough energy is transferred so that each increases its temperature by 20 degrees C. So the answer is iron, then glass, and then water. So for a given temperature increase, the energy transferred by heat is proportional to the specific heat. So let's start to get into calories. This is a diagram of a calometer. And so you might wonder how specific heat is determined for a substance. Calometry is a technique for measuring the specific heat of a solid or liquid. First, a substance is placed in a well-insulated vessel called a calometer, like the one shown in the figure. Since the calometer is insulated, we assume energy doesn't leave the system. We say the system is isolated. That means if one part of the system loses energy, another part has to gain the energy because the energy has nowhere else to go. For example, when a warm object is placed in a cooler water of a calometer, the warm object becomes cooler while the water becomes warmer. The principle can be written as shown. Q cold is positive because the energy is flowing into the cooler objects, and Q hot is negative because energy is leaving the hot object. The negative sign on the right-hand side of this equation ensures that the right-hand side is a positive number consistent with the left-hand side. Remember, this equation is valid only for isolated systems. Sometimes there are lots of substances exchanging thermal energy, and each with a different temperature. We can still use our equation if we are careful. Let's suppose we want to calculate the final temperature of a system consisting initially of a glass beaker at 25 degrees C, hot water at 40 degrees C, and a block of aluminum at 37 degrees C. We know that after the three are combined, the glass beaker warms up and the hot water cools, but we don't know for sure whether the aluminum block gains or loses energy because we don't know the final temperature. With an unknown final temperature, T sub F, our expression for Q will be positive if T sub F is greater than T sub I, and negative if T sub F is less than T sub I. So we can write the equation for the sum of the energy as shown, where Q sub K is the energy change in the kth object. Each term will have the correct sign automatically. Applying this equation to the water, aluminum, and glass problems, we get the equation. There's no need to decide in advance whether a substance in the system is gaining or losing energy. This equation is similar in style to the conservation of mechanical energy equation, where the gains and losses of kinetic and potential energy sum to zero for an isolated system. So moving on. So generally, when energy is transferred between a substance and the environment, the temperature of the substance changes. But when the substance undergoes a phase change, which means that its physical characteristics change from one form to another, the transfer of energy doesn't result in a temperature change. Examples of phase changes are when a solid melts, forming a liquid, when liquid boils, forming a gas, or a change in a crystalline structure of a solid. Sublimation is a phase change when solid goes directly to gas phase without going through a liquid phase. A phase change involves a change in the internal energy, but no change in the temperature. The energy Q needed to change the phase of a given pure substance is shown here, where L, they're called the latent heat of the substance, depends on the substance and the nature of the phase change. The word latent means lying hidden within a person or thing. The positive sign in this equation is for when energy is absorbed by a substance, for example, when ice is melting. The negative sign is for when energy is removed from a substance, for example, when steam condenses to water. The latent heat of fusion, L sub F, is used when a phase change occurs during melting or freezing, and the latent heat of vaporization, L sub V, is used when a phase change occurs during boiling or condensing. For example, at atmospheric pressure, the latent heat of fusion for water is 3.33 times 10 to the 5 joules per kilogram, and the latent heat of vaporization for water is 2.26 times 10 to the 6 joules per kilogram. The table shows the latent heats for some substances. Note that the values can vary a lot. So in this figure, we have a plot of temperature versus energy added when a 1 gram of ice initially at 230 degrees C is converted to steam at 120 degrees C. So let's think about adding energy to a 1 gram cube of ice at minus 30 degrees C in a container held at constant pressure. Suppose this input of energy turns the ice to steam or water vapor at 120 degrees C. The figure is a plot of the experimental measurement of temperature as energy is added to the system. Let's examine each portion of the curve separately. So first we'll look at part A. It's a small part there. During this portion of the curve, the temperature of the ice changes from minus 30 degrees C to 0 degrees C. Because the specific heat of ice is 2090 joules per kilogram C, we can calculate the amount of energy added. So in part B, this is when the ice reaches 0 degrees and the ice water mixture remains at that temperature, even though energy is being added until the ice melts to become water at 0 degrees C. Now let's calculate the energy required to melt 1 gram of ice at 0 degrees C. So in part C, between 0 degrees C and 100 degrees C, no phase change occurs. The energy added to the water is used to increase its temperature as it did in part A. Now we can calculate the amount of energy to increase the temperature from 0 degrees to 100 degrees C. We see that in the equation. So in part D, at 100 degrees C, another phase change occurs as the water changes to steam at 100 degrees C. As in part B, the water-steam mixture remains at a constant temperature, this time at 100 degrees C, even though energy is being added until all the liquid has been converted to steam. So let's calculate the energy required to convert 100 grams of water to 100 grams of steam at 100 degrees C, and that's the equation there on the bottom. And then for part E, during the portion of this curve as parts A and C, no phase change occurs, so all the added energy goes into increasing the temperature of the steam. Finally, we can calculate the energy that must be added to raise the temperature of the steam to 120 degrees C, and that's shown in the equation. So the total amount of energy that must be added to change 1 gram of ice at minus 30 degrees steam, 100 at minus 30 degrees C to steam at 120 degrees C is the sum of the result of all 5 parts of the curve, which is 3,110 joules. On the other hand, to cool 1 gram of steam at 100 degrees C to the point at which it becomes ice, to cool to minus 30 degrees C is once again the same thing, 3,110 joules of energy that must be removed. So in this figure, we're seeing a crew of US Coast Guard's cutters heli dipping their feet in a melt pond during NASA's IceScape Impacts of Climate on ecosystems and chemistry of the Arctic Pacific Environment Mission. So cute picture. We think of phase changes in terms of rearrangements of molecules when energy is added to or removed from a substance. Let's first consider the liquid to gas phase change. So the molecules in a liquid are closer together. They're close together, and the forces between them are stronger than the forces between the gas molecules, which are more widely separated. This means work must be done on the liquid against these attractive molecular forces to separate the molecules. The latent heat of vaporization is the amount of energy that must be added to the 1 kilogram of liquid to accomplish this. In a similar way, at the melting point of a solid, the amplitude of vibration of the atoms about their equilibrium position becomes great enough to allow the atoms to pass the barriers of adjacent atoms and move to their new positions. On average, these new positions are less symmetrical than the old ones and so have higher energy. The latent heat of fusion is equal to the work required at the molecular level to transform the mass from the ordered solid phase to the disordered liquid phase. The average distance between atoms is much greater in the liquid phase than in either the liquid or the solid phase. Each atom or molecule is removed from its neighbors and comes the attractive force of nearby neighbors. That means that more work is required at the molecular level to vaporize a given mass of a substance than to melt it. So in general, the latent heat of vaporization is much greater than the latent heat of fusion. So let's have a question here. So calculate the slopes for A, C, and E portion of the figure. Rank the slopes from least to greatest. Okay, the answer is going from C, going to A, and then E. And so the slopes are proportional to the reciprocal of the specific heat. So large specific heat results in a smaller slope, meaning more energy to achieve a given change in temperature. So I apologize that the figure is not there, but we'll just skip over that to fix that. So here is, let's talk about a problem solving strategy for calorimetry with phase changes. And so there's 3 steps. So the first is make a table for all data, include separate rows for different phases, and for any transition between phases, include columns for each quantity used and a final column for the combination of these quantities. Transfers of thermal energy in this last column are given by the first equation shown, and phase changes are given by the second equation for the changes between liquid and solid, and by the third equation for changes between liquid and gas. So that's number 1. Number 2, apply conservation of energy. If the system is isolated, use this equation. For a non-isolated system, the net energy change should replace the 0 on the right-hand side of the equation. Here, the expression on the left is just the sum of all the terms in the last column of the table. And finally, we solve for the unknown quantities. Sometimes solving problems involve changes in mechanical energy. During a collision, for example, some kinetic energy can be transformed to the internal energy of the colliding objects. So here we have a picture of maybe something fairly familiar to you, stovetop. And so we have an electric stovetop in this situation rather than gas. And so conduction makes the metal handle of a cook pan hot. And so for thermal conduction or conduction, it's the energy transfer process which most closely associated with the temperature difference. In this process, we can think of the transfer of the atomic scale as an exchange of kinetic energy between microscopic particles, that is molecules, atoms, and electrons, with less energetic particles gaining energy as they collide with more energetic particles. Take a look at the photo. The pot has an insulated metal handle. When the pot is warm, the temperature of the metal handle increases, and the cook must hold it with a cloth pot holder to avoid being burnt. We can understand that the way the handle warms up by looking at what happens to the microscopic particles in the metal. Before the pot is placed on the stove, the particles are vibrating about their equilibrium position. As the stove coil warms up, those particles in contact with it begin to vibrate with larger amplitudes. These particles collide with their neighbors and transfer some of their energy in their collisions. Metal atoms and electrons farther and farther from the coil gradually increase the amplitude of the vibrations, till eventually those in the handle are affected. This increased vibration represents an increase in temperature of the metal. Even though the transfer of energy through a substance can be partly explained by atomic vibrations, the rate of conduction depends on the properties of the substance. For example, it's possible to hold a piece of asbestos in a flame indefinitely, which implies that very little energy is conducted through the asbestos. In general, metals are good thermal conductors because they contain large numbers of electrons that are relatively free to move through the metal and can transport energy from one region to another. In a good conductor like copper, conduction takes place through the vibration of the atoms and the motion of free electrons. Materials like asbestos, cork, paper, and fiberglass are poor thermal conductors. Glasses are also poor thermal conductors because of the large distance between their molecules. So in this figure, we're looking at energy transfer through a conducting slab of cross-sectional area A with thickness delta X. And so this part of thermal conduction, we're thinking about conduction occurs only if there is a difference in temperature between two parts of the conducting medium. The temperature difference drives the flow of energy. Think about a slab of material of thickness delta X and cross-sectional area A with its opposite phases and at different temperatures, TC and TH. Where TH is greater than TC, as you can see in the figure, the slab allows energy to transfer from the region of the higher temperature to the region of the lower temperature by thermal conduction. The rate of thermal transfer P is proportional to the cross-sectional area of the slab and the temperature difference, and is inversely proportional to the thickness of the slab. Note that P has units of watts, where Q is in joules and delta T is in seconds. So in this figure, we're looking at conduction of energy through a uniform isolated rod of length L. So let's suppose a substance is in the shape of a long uniform rod of length L, as in the figure. Let's assume that the rod is isolated, so thermal energy can't escape by conduction from the surface except at the ends. One end is in thermal contact with an energy reservoir at temperature Tc, and the other end is in thermal contact with a reservoir temperature of Th, which is greater than Tc. Eventually, the system reaches a steady state, which means that the temperature at each point along the rod is constant in time. In this case, we have the relationship shown. The rate of energy transfer by conduction through the rod is given by the equation here, which is K, the thermal conductivity, and is a proportionality concept that depends on the material. Substances that are good conductors have large thermal conductivities, and good isolators have low thermal conductivities. So here we have a table that lists the thermal conductivities for various substances, and so you can just keep that in mind. So let's have another question here. So compared to an identical ice cube exposed to air at room temperature, an ice cube wrapped in a wool blanket remains frozen for, the answer is for a longer time. The blanket acts as a thermal insulator, slowing the transfer of energy by heat from the air into the cube. Here's another question, and two rods of the same length and diameter are made from different materials. The rods are to connect two regions of different temperatures so that energy will transfer through the rods by heat. They can be conducted in series or as in figure A in parallel, or as in figure B in case where the energy is transferred by heat transfer. So We're just basically trying to compare these two in parallel versus in series. And the answer is when they are in parallel. So the rate of energy transfer by conduction through a rod is proportional to the difference in the temperature at the ends of the rod. When the rods are in parallel, each rod experiences a full difference in the temperature of the two regions. If the rods are conducted in series, neither rod will experience a full temperature difference between the two regions, and hence neither will conduct energy as rapidly as it did with a parallel connection. There's more surface area for these to conduct heat, and so that might be another perspective for you to be thinking about. So now we're thinking about home insulation. Might be another practical application that you have some familiarity with. And so a worker installs fiberglass insulation in a home. The mask protects the worker against the inhalation of microscopic fibers, which could be hazardous to his health. So let's say that you want to decide whether or not to add insulation to some part of a building. We need to think about a few more details. And so number one, the insulation properties and materials used in the building are usually expressed in engineering units. That is US custom made rather than SI units. Measurements stamped on the package of a fiberglass insulating board will be in units such as British thermal units, BTUs, and feet and degrees Fahrenheit. So number two, when dealing with the insulation of buildings, we need to consider conduction through a compound slab, with each portion of the slab having a certain thickness and specific thermal conductivity. A typical wall in a house consists of different materials, for example, wood paneling, drywall, insulation, sheathing, and wood siding. The rate of energy transfer by the conduction through a compound slab is given in the equation that we're showing here. So the R values for a few common building materials are listed in the table. So if you were going to Home Depot or Lowe's or some other hardware store, you might be seeing that. And so note that the unit of R and the fact that the R values are defined by specific thicknesses. Next to any vertical outside surface is a very thin stagnant layer of air that will also need to consider when we compute the total R value for a wall. The thickness of the stagnant layer depends on the speed of the wind. As a result, energy lost by conduction from a house on a day when the wind is blowing is greater than the energy loss on a day when the wind speed is 0. So the values are typically in British units, but they can be converted to the equivalent metric units by multiplying the value in the table by 0.1761, as we show here in the bottom. So here we're getting a chance to see warming, how you would experience that by putting your hand close to a flame. So if we take a look at this figure, when you warm your hands over an open flame, the air directly above the flame expands because it is being warmed. This means that the density of this air decreases and the air masses warms your hand as it flows by. The transfer of energy by the moment of a substance is called convection. When the movement results from differences in density, as with air around a fire, it is a reference to the natural convection. Airflow at a beach is an example of natural convection, and it's a mixing that occurs as the surface water in a lake cools and sinks. So here we have a photograph of a tea kettle showing steam and the turbulent convection air currents that are coming out. And so when a substance is forced to move by a fan or pump, as in some hot air and hot water heating systems, the process is called forced convection. So if we look at the photo, the convection currents help water to boil. In a tea kettle on a hot stovetop, the lower layer of water are warmed first. The warm water has a lower density and rises to the top, while the denser, cooler water on the surface sinks to the bottom of the kettle and is warmed. So here now we're looking at a house, looking at the convection currents that are set up by a room warmed by a radiator. So the same process occurs when the radiator raises the temperature of the room. The hot radiator warms the air in the lower region of the room. The warm air expands, and because of its lower density, rises to the ceiling. The denser, cooler air from above sinks, setting up the continuous air current pattern shown in the figure. An automobile engine is maintained at a safe operating temperature by combination of conduction and forced convection. Water, or rather a mixture of water and antifreeze, circulates in the interior of the engine. As the metal of the engine block increases in temperature, energy passes from the hot metal to the cooler water by thermal conduction. The water pump forces water out of the engine into the radiator, and in the process carries energy along with it. That is by forced convection. In the radiator, the hot water passes through metal pipes that are in contact with cooler outside air, and energy passes into the air by conduction. The cooled water returns to the engine by the water pump to absorb more energy. The process of the air being pulled past the radiator by the fan is also forced convection. So here we're looking at a figure that the top figure, during the summer, a warmer upper layer of water is separated from a cooler layer by a thermocline, and the below convection currents during the spring and fall mix the water and can cause algae blooms. So just a couple of things that you might have experienced. And so you may have seen algae blooms in a lake or ponds during the spring or fall. These are caused by convection currents in the water. So if you take a look at the figure in more detail, during the summer, bodies of water develop temperature gradients with a warm upper layer of water separated from a cooler lower layer by a buffer zone called a thermocline. In the spring and fall, the temperatures change and the water breaks down the thermocline, setting up convection currents that mix the water. The mixing process transports nutrients from the bottom to the surface. The nutrient-rich water forming at the surface can cause a rapid temporary increase in the algae population. So here we're looking at warming one's hands by some form of radiation, whether it be an incandescent light bulb or something else. And so another process of transferring energy is through radiation. The figure shows how your hands can be warmed by a lamp through radiation. Because your hands aren't in physical contact with the lamp, the connectivity of the air is very low. Conduction can't account for the energy transfer, nor can convection be responsible. Because your hands aren't above the lamp in the path of convection currents. The warmth felt in your hands must come from the transfer of energy by radiation. All objects radiate energy continuously in the form of electromagnetic waves due to thermal vibrations of their molecules. These vibrations create the orange glow of an electric stove burner, an electric space heater, and the coils of a toaster. The rate at which an object radiates energy is proportional to the fourth power of its absolute temperature. This is known as Stefan's law, expressed in equation form as shown, where P is the power in watts radiated by the object. Rho is the Stefan-Boltzmann constant, and A is the surface area of the object in square meters. E is a constant called the emissivity of the object, and T is the object's Kelvin temperature. The value of E can vary between 0 and 1 depending on the properties of the object's surface. So here we have a figure of looking at the Earth from Gemini 7. So about 1,370 joules of electromagnetic radiation from the sun pass through each square meter at the top of the Earth's atmosphere every second. This is radiation, is mainly visible light and the significant amount of infrared and ultraviolet light. We will study these topics of radiation detail in a later topic. Some of the energy is reflected back into space and some is absorbed by the atmosphere, but enough arrives at the surface of the Earth each day to supply all our energy needs hundreds of times over, and it could be captured and used efficiently. Thus, things like solar panels are a nice thing. So think about what happens to the atmosphere temperature at night. If there is a cold cover above the Earth, the water vapor in the clouds absorb part of the infrared radiation emitted by the Earth and re-emits it back to the surface. For this reason, the temperature at the surface remains at moderate levels. In the absence of cloud cover, there is nothing to prevent radiation from escaping into space, so the temperature drops more on a clear night than on a cloudy night. So as an object radiates energy, it also absorbs radiation. If it didn't, the object would eventually radiate all its energy and the temperature would reach absolute zero. The energy an object absorbs comes from its environment, which consists of other bodies that radiate energy. If an object at temperature T and its surrounding area at temperature T0, the net energy gain or loss each second by the object as a result of radiations is given in this equation that we're showing. When an object is at equilibrium with its surroundings, it radiates and absorbs energy at the same rate, so its temperature remains constant. When an object is hotter than its surrounding, it radiates more energy than absorbs and therefore cools. An ideal absorber is an object that absorbs all of the radiation incident on it, including invisible, infrared, and ultraviolet light. This object is called a black body because a room temperature black body would look black. Because a black box doesn't reflect radiation at any wavelength, any light coming from it is due to atomic molecular vibrations alone. A perfect black box has emissivity of E = 1. An ideal absorber is an ideal radiator of heat. The sun, for example, is nearly a perfect black body. The statement may seem contradictory because the sun is bright, not dark. The light that comes from the sun, but remember, the sun's light is emitted, not reflected. So black bodies are perfect absorbers that look black at room temperatures because they don't reflect any light. All black bodies, except those at absolute zero, emit light that has a characteristic spectrum, which we will talk about in a later topic. So on the other hand, an object for which the emissivity E = 0 is absorbed none of the energy incident on it, reflecting at all. Such a body is an ideal reflector. White clothes clothing is more comfortable to wear in the summer than black clothing. Black fabric acts as a good absorber of incoming sunlight and as a good remitter of the absorbed energy. About half of the emitted energy, however, travels towards the body, causing the person wearing the clothes to feel uncomfortably warm. White or light colored clothing reflects away much of the incoming energy. So we saw this on the cover for this week, and this is showing a thermogram of a house made during cold weather. So the amount of energy radiated by an object can be measured with a thermogram, which is an image of the pattern formed by varying radiation levels. In a thermogram, the brightest areas are the warmest, as you can see in the photo of a house. It is clear that more energy escapes in the lighter region, which is through the doors and windows. The owners of this house could conserve energy and reduce their heating costs by adding insulation to the attic areas and by installing thermal draperies over the windows. So in this figure, we have a thermogram of a woman's breast. Her left breast is diseased. There's a red and orange, and her right breast is blue, is healthy. So thermograms have also been used to image injuries or diseased tissues in medicine, as shown in this figure, because these areas are often at a different temperature than standard healthy tissue, although many radiologists consider thermograms inadequate as a diagnostic tool. So in this figure, we have a radiation thermometer measuring a patient's temperature by monitoring the intensity of infrared radiation leaving the ear. So the figure shows this radiation thermometer. So it's measuring the intensity of the infrared radiation leaving the eardrum and the surrounding tissue and converts this information to a standard numerical reading. The eardrum is a particularly good location to measure body temperature because it's near the hypothalamus, the body temperature's control center. So here's a question: is stars A and B have the same temperature, but star A has twice the radius of star B? What is the ratio of star A's power output to star B's output due to the electromagnetic radiation? The emissivity of both stars can be assumed to be 1. So the answer is PA over PB equals 4. And so from Stefan's law, the power radiation from an object at absolute temperature T is proportional to the surface area of that object. Surface A, star A has twice the radius and thus 4 times the surface area of star B. So here's another one. So star A has twice the absolute temperature of star B, but both have the same radius. What is the ratio of star A's power output to star B's power output due to electromagnetic radiation? The answer is PA over PB equals 16. And so from Stefan's law, the power radiation from an object having surface area A is proportional to the 4th power of the absolute temperature. And thus, if we just use Stefan's law, do a little bit of math, we're going to get that PA is 16 TB. And so that's where we get this answer. If you have the ratio and the difference, and so it would be a difference of 16. So here star A has twice the absolute temperature, twice the radius. What is the ratio of stars A power output to star B's output due to electromagnetic radiation? And so the answer is 64. And when a star has both twice the radius and twice the absolute temperature of star B, the ratio of the radiated powers, if you just use Stefan's law and taking the ratio and do some simplification, you'll find that the answer is 64. Okay, let's talk about the Dewar flask. And so here we're seeing a cross-sectional view of a thermal bottle designed to store hot or cold liquids. So we're looking at a Dewar flask, which is designed to minimize the energy transfer by conduction, convection, and radiation. A thermos bottle is an example of a Dewar flask. The insulated bottle can store either hot or cold liquids for long periods. The standard vessel is a double-wall Pyrex glass with silvered walls. The space between the walls is evacuated to minimize energy transfer by conduction and convection. The silver surface minimizes energy transfers by radiation because silver is a very good reflector and it has very low emissivity. Dewar flasks are commonly used to store liquid nitrogen, which has a boiling point of 77 Kelvin, and liquid oxygen, which has a boiling point of 90 Kelvin. To confine liquid helium, which has a boiling point of 2.4 Kelvin and a very low heat of vaporization, is often necessary to use a double Dewar system in which the Dewar flask contains a liquid is surrounded by a second Dewar flask. The space between the two flasks is filled with liquid nitrogen. Some of the principles of the thermal bottle are used in the protection of sensitive electronic instruments in orbiting space stations, and half of its orbit around the Earth, the satellite is exposed to intense radiation from the sun. And the other half, it lies in the Earth's cool shadow. Without protection, the interior would be subjected to tremendous extremes of temperature. The interior of the satellite is wrapped with blankets of highly reflective aluminum foil. The foil's shiny surface reflects away much of the sun's radiation while the satellite is in the unshaded part of the orbit and helps retain interior energy while the satellite is in the Earth's shadow. So let's talk about garden greenhouses. And so in a garden greenhouse, let's get a chance to explore how it works. During the day, sunlight passes into the greenhouse and it is absorbed by the walls, the soil, and the plants. This absorbed visible light is radiated as infrared radiation, causing the temperature of the interior to rise. Convection currents are inhibited in a greenhouse. As a result, warmed air can't rapidly pass over the surface of the greenhouse that are exposed to the outside air, and so there is little energy loss by conduction through those surfaces. Most experts now consider this restriction to be a more important warming effect than the trapping of infrared radiation. In fact, experiments have shown that when the glass over a greenhouse is replaced by a special glass node to transmit infrared light, the temperature inside is lowered only slightly. On the basis of this evidence, a primary mechanism that raises the temperature of the greenhouse is not the trapping of infrared radiation, but the inhibition of airflow that occurs under any roof in an attic, for example. A phenomena commonly known as the greenhouse effect can also play a major role in determining the Earth's temperature. First, note that the Earth's atmosphere is a good transmitter, which means a poor absorber of visible radiation and a good absorber of infrared radiation. The visible light that reaches the Earth's surface is absorbed and re-radiated as infrared light, which in turn is absorbed or trapped in the Earth's atmosphere. So in this figure, we're looking at the concentration of atmospheric carbon dioxide in parts per million of dry air as a function of time during the latter part of the 20th century. These data were recorded at Maui Loa Observatory in Hawaii. The yearly variations, which is the rust-colored curve, coincide with growing seasons because vegetation absorbs carbon dioxide from the air. The steady increase, which is the black curve, is of concern to scientists. As fuel fossils such as coal, oil, and natural gas are burned, large amounts of carbon dioxide are released into the atmosphere, causing it to retain more energy. These emissions are of concern to some scientists and government throughout the world. Many scientists are convinced that 10% increase in the amount of atmospheric carbon dioxide since 1970 could lead to drastic changes in the world climate. Increasing concentration of atmospheric carbon dioxide in the latter part of the 20th century and the first years of the 21st century is shown in this figure. According to one estimate, doubling the carbon dioxide content in the atmosphere will cause the temperature to increase by 2 degrees Celsius. In temperate regions such as Europe and the United States, a 2 degrees temperature rise would save billions of dollars per year in fuel costs. Unfortunately, it would also melt a large amount of land-based ice from Greenland and Antarctica, raising the levels of the oceans and destroying many coastal regions. A 2 degrees rise would also increase the frequency of the droughts and consequently decrease already low crop yields in tropical and subtropical countries. Even slightly higher temperature, average temperatures might make it impossible for certain plants and animals to survive in their customary ranges. So anyway, just a fair amount of things that you can be thinking about with the changing in the environment. Some would argue that there isn't an overall trend, that this could be just an Earth type of trend that has taken place, and maybe the human component might be a smaller area. And so this is a picture of looking at how an ice shelf has changed over time. And so we have a figure in 1995. And so that's one figure. And then having seen that change, I'm just going to go and skip over this, but this is still on that same theme. So let's do a little bit of an assessment of learning here. Have a handful of questions, and then we'll finish up for this lecture. And due to time, I'm just going to give the answers, and you can be thinking about these. And so which of the following phrases best describes heat? And the answer is the total energy flowing between two bodies at different temperatures. And for this, two objects made from the same material have different masses and different initial temperatures as shown. If the bodies are placed in thermal contact, the final equilibrium temperatures is mostly near, and the answer is 47 degrees C. So next question is, to have your coffee be as hot as possible when you drink it later, when should you add room temperature cream? And the answer is as soon as the coffee is served. Two identical thermodynamic systems, one at T1 and one at T2, were placed in thermal contact. When they reach thermal equilibrium, what is true about the final temperature? And the answer is T final is 1/2 of the quantity T1 plus T2. By what factor would the total power from a black body be modified if the surface area were to decrease by a factor of 2 while the temperature was doubled? The answer is 8. And so with that, we just have 2 slides for topic summary, and then we'll be finished for this lecture. So for heat and internal energy is associated with the system's microscopic components. Internal energy includes the kinetic energy of translation, rotation, and vibration of molecules, as well as potential energy. Heat is a transfer of energy across the boundaries of a system, resulting from a temperature difference between the system and its surrounding. The symbol Q represents the amount of energy transferred. The calorie is the amount of energy necessary to raise the temperature of 1 gram of water from 14.5 degrees C to 15.5 degrees C. The mechanical equivalent of heat is 4.186 joules per calorie. For specific heat and calorimetry, the energy required to change the temperature of a substance of mass M by amount delta T is shown here, where C is specific heat of the substance. In calorimetry problems, the specific heat of a substance can be determined by placing it in water of known temperature, isolating the system, and measuring the temperature at equilibrium. The sum of all energy gains and losses for all objects in an isolated system is given by the equation shown, where Q sub K is the energy change in the kth object in the system. This equation can be solved by the unknowns specified here or used to determine an equilibrium temperature. For latent heat and phase change, the energy required to change the phase of pure substance of mass M is shown here, where L is the latent heat of the substance. The latent heat of fusion, L sub F, describes an energy transfer during a change from a solid phase to a liquid phase or vice versa, while the latent heat of vaporization, LV, describes the energy transfer during a change from liquid phase to a gaseous phase or vice versa. Calorimetry problems involving phase changes are handled with a sum of Q with latent heat terms added to the specific heat terms. For energy transfer, energy can be transferred by several different processes, including work and by conduction, convection, and radiation. Conduction can be viewed as the exchange of kinetic energy between colliding molecules or electrons. The rate at which energy transfers by conduction through a slab of area A and thickness L is given here, where K is the thermal conductivity of the material making up the slab. Energy is transferred by convection as a substance moves from one place to another. All objects radiation from their surface in the form of electromagnetic waves at a net rate of P net, where T is the temperature of the object and T0 is the temperature of the surroundings. An object that is hotter than its surrounding radiates more energy than it absorbs, whereas a body that is cooler than its surrounding absorbs more energy than it radiates. Okay, well, that's it for this lecture. Thank you very much.